welcome to this explainer on NCP-MCI 7.5, specifically Objective 14.6, Validating Capacity Under Failure and Disaster Recovery. We're going to dive deep into exam prep for the Nutanix NCP-MCI certification, focusing strictly on the baseline AOS 7.5, AHV 11.0, and Prism Central 7.5 environments. Listen, if you're an infrastructure admin gearing up for this exam, this is one subtopic you absolutely cannot skip. Nailing this objective is really what separates the novices from the experts. Why? Because it bridges that crucial gap between what your cluster looks like on a perfectly normal Tuesday and what it mathematically requires to survive a catastrophic failure.
So before we get into the heavy math, I want you to think about this question. If your absolute largest, most heavily loaded node literally catches fire right now, do you actually have the physical capacity to recover? Because on the exam, and let's be honest, in the real world, hoping for the best just isn't a strategy. When the alarms start blaring, your cluster is relying on cold, hard math to self-heal. We need to make sure you know exactly how that math works. Validating capacity is all about proving, definitively, that your environment can self-heal without taking your production workloads down with it.
Here's our roadmap for this explainer. 1. Why capacity validation matters. 2. Compute walkthrough focusing on HA memory. 3. Storage walkthrough looking at rebuild capacity. 4. Common exam traps. And 5. Key facts to memorize.
Okay, let's jump right into Section 1, Why Capacity Validation Matters. If you get your capacity calculations wrong, you're setting yourself up for cascading failures, which translates directly to failing those tricky scenario-based exam questions. Let's break down 3 core concepts here. First up is HA, or high availability, which ensures that if a host dies, your virtual machines, your VMs, can actually restart on healthy nodes. Then there's DR, or disaster recovery, which is your site-level protection from massive outages. And finally, CCLM, or cross-cluster live migration, which allows for zero downtime workload movement across fault domains. But here is the massive catch for all 3 of these. They are 100% dependent on having guaranteed, reserved resources just waiting to catch those moving workloads. Think about CCLM for a second. If you're live migrating workloads across clusters to avoid downtime, the receiving cluster mathematically has to have the space to catch them without degrading performance. If you haven't validated that capacity up front, well, none of these features are going to save you.
To put that into perspective, think about a metro availability setup with a witness service sitting at the top, completely automating failover if your primary domain goes dark. You've got your primary data center and a DR site, securely linked with synchronous replication for a 0 RPO, or recovery point objective. Sounds bulletproof, right? But true 0 RPO disaster recovery absolutely requires guaranteed compute and storage resources waiting at that DR site. If your DR site is already running hot, say at 90% capacity with its own daily workloads, it physically cannot accept the replicated VMs from the primary site during a failover. The failover process will just stall out, and your recovery will completely fail.
Moving right along to Section 2, let's walk through the compute side of things, specifically HA memory.
When a node drops offline, the cluster has to react in milliseconds. This heavy lifting is handled by ADS, or Acropolis Dynamic Scheduling. ADS is the brain that identifies healthy hosts to restart your VMs on during an HA event. But for ADS to actually pull this off, 100% of the configured memory of those orphaned VMs must be available somewhere else in the cluster. When you're sitting down for the exam, you have to assume ADS needs these resources immediately. It's not going to sit around waiting for a ballooning driver to slowly free up memory on other hosts. No, it relies entirely on the memory you have explicitly reserved ahead of time to bring those VMs back to life.
So how exactly does AHV carve out and reserve that memory? Well, to provide those guaranteed restarts, AHV uses a feature called Guarantee Mode, which leverages segment-based reservation. It follows 3 specific steps. First, the scheduler divides the total cluster memory into segments. Second, and you absolutely need to remember this for the test, it matches the segment size to the single largest VM it guarantees to restart. And third, it calculates the host failure tolerance to make sure enough of those segments are set aside. Let's say you have 50 standard 4 GB VMs and 1 massive 32 GB database VM. The cluster builds that segment size entirely around that 32 GB behemoth. By basing the math on the largest VM, AHV ensures that no matter which node fails, even your biggest, most demanding VM will always have a physical place to land.
Now, this is where things get really interesting and, honestly, pretty costly from a capacity standpoint. Starting in AAV 6.0, AHV introduced memory overcommit.
But if you combine guarantee mode HA with memory overcommit, you are going to get hit with a massive capacity penalty. Because overcommitted VMs don't have all their configured memory backed by physical RAM during normal, everyday operations, the cluster has to reserve a whopping 75% chunk just to guarantee they can safely spin back up during a failure. Memorize this exact percentage. 75% of the configured memory for those overcommit-enabled VMs is strictly cordoned off. That leaves you with only 25% for available usage. This severely reduces your total usable cluster memory, meaning your theoretical maximum for overcommit drops like a rock when HA is enabled.
All right, let's shift gears from compute over to storage for Section 3, rebuild capacity.
Rebuild capacity reservation is basically storage capacity that is explicitly held back from your usable pool. When you toggle on the Reserve Rebuild Capacity option in Prism Element, the system actively subtracts that required capacity from your available storage. This is the magic that enables self-healing. Think about it. If you don't explicitly carve out this space, your cluster might just eat it up for normal VM data over time. Then, when a failure actually happens, your cluster is physically unable to rebuild the data, leaving you stuck in a permanently degraded state. But if you reserve it correctly, a node can fail, and the cluster will use this dedicated space to instantly replicate and rebuild the lost data across the remaining healthy nodes without bringing your production environment to its knees.
The real trick here is calculating exactly how much storage gets held back. For an n+1 scenario, meaning an architecture with 1n over 1 default tolerance, which tolerates one node or one disk failure, you have to reserve the exact capacity of the single largest node in the cluster. Why the largest? Because you always have to plan for the worst-case scenario. What if your most data-heavy node is the one that catches fire? The exam is absolutely going to try to trick you here by asking if you should use the average node capacity. Don't fall for it. It's always the largest node. And if you're running a 2n2 default tolerance setup, well, then you have to reserve the capacity of the two largest nodes.
While we're on the topic of fault tolerance, you need to pay close attention to replication factor, or RF. Nutanix explicitly recommends replication factor 3 for optimal resiliency. And the reason is simple. With replication factor 2, your containers can only survive the failure of a single node or a single disk. Let's look at a very common practical exam scenario. If you're running RF2 and you put a node into maintenance mode to do some upgrades, you have effectively zero fault tolerance left. A single disk failure on any other node at that exact moment means immediate data unavailability.
Okay, that brings us to Section 4, Common Exam Traps. Let's walk through the minefield.
This first one is a classic gotcha. Do not let the dashboards trick you on a scenario question. When HA is enabled, Prism Element actually shows you different memory values depending on where you look. The Home Dashboard's Cluster Memory Usage widget includes the memory that's reserved for HA failover. But if you pop over to the Analysis dashboard, the Hypervisor Memory Usage graph entirely excludes that HA reserved memory. It's only showing you what is actively being consumed by the hypervisor and running VMs. The logic is actually pretty straightforward once you know it. The Home Dashboard gives you the physical reservation reality of your cluster, while the Analysis dashboard gives you the live active load. Just read the exam question very carefully to know which one they're testing you on.
Here's another massive exam trap regarding how the cluster self-heals: node failures versus disk failures. They do not trigger the exact same response. If a whole node goes dark, the system doesn't immediately panic and initiate a massive data rebuild. It waits. By default, it waits to see if the node comes back online. Because hey, maybe it's just a temporary network blip or a quick host reboot. Kicking off a massive data migration immediately would just crush cluster performance for no reason. But a failed disk? That's hardware death. There's no coming back from that, so the rebuild kicks off immediately to restore your resiliency before another failure can take you down. Make sure you know that difference.
All right, we are in the home stretch. Section 5, Key Facts to Memorize.
Lock these 4 things into your brain before test day, and you're going to sail right through Objective 14.6. First, segment-based HA always reserves capacity based on the largest VM. If they mention average VM size, they're tricking you. Second, guarantee mode hits you with a massive 75% memory reservation penalty for overcommit-enabled VMs. Keep that in mind if you're designing with overcommit. Third, the cluster memory usage metric on the Home Dashboard is the one that includes your HA reservation. And finally, a 1N 1D storage configuration demands that you reserve the rebuild capacity of the single largest node, not the average.
I want to leave you with a final thought as you wrap up your prep for the NCP-MCI 7.5 exam. Think about your own environment for a second. Is your cluster's N+1 plan truly relying on the hard math of active reservations, or are you just kind of hoping your largest node never goes down? Validating capacity under failure is entirely about removing hope from the equation and replacing it with guaranteed resources. Good luck on the exam, keep these rules in mind, and make sure your infrastructure is mathematically ready for whatever comes its way.